All right, so here we go. We have our derivative rules video. This is our very first one, and this one is our power rule. We'll also be talking about our constant rule in here because they do go hand in hand if you can see the connection. So here is our power rule. So we always have this notation. This notation means, oops, I'm gonna make that a different color. This notation means the derivative, okay? So that means that we're taking the derivative of this function, or maybe a piece of a function. And that means that we're taking the derivative with respect to x, okay? Meaning that x is our variable here. So d dx just means I'm taking the derivative of my x variable. So we have this power rule. So our power rule is for when we have maybe x to a power, which should make sense, that's the name. So we have our power rule, and what we do to find this derivative, you take your power and you multiply it to the front, and then you subtract 1 from your power. So you bring that power down, multiply it to the front, and then you subtract 1 from your exponent, and that would be your new term, or the term in your derivative. So a quick tiny little example of this would be maybe if we had example, we needed to find the derivative of x to the 7th. Okay, so that means that I'm going to take my 7 to the front, and then I'm going to subtract 1 from my exponent. So this is really going to be 7x to the 6th, and that would be our solution there. Okay, so here we have some examples. You can see some already done out. We're going to look at them in a second. And we'll start with number 1. So I had mentioned earlier that we will see constants in this rule as well. And there really is something called a constant rule, but it really does go hand in hand with the power rule. When you have a constant, you can imagine what variable you had there. So I'm just going to write this bigger so we can see it. So we have y equals 5 is our function here. It's just a horizontal line. Now you can think about derivatives as the slope of the tangent line, okay? So the slope of a tangent line, or the slope of a horizontal line, is 0. So I'm expecting this to become 0. So when I'm looking at this and I'm trying to figure out what to do with my variable of x, I don't see an x. So what that really means to us is that this is really like x to the 0 power, okay? So that's anything to the 0 power is 1. It's just not truly there because it's a 1 instead of an x to the 0. So you can see how this works with our power rule, is that what we're going to do is we're going to take this 0 and multiply it to the front. And at this point, it really does not matter about anything else because I have all of these terms multiplied by 0. So that means that my y prime, or my derivative of y, will be 0. So this is kind of like a little important little side note you want to make sure that you write down. Okay, so it's like a little side note. And this is for constants, okay? And you're going to see that we have constants in the rest of our problems, at least one of these, but you'll see them online too. And our side note is that if we want to take the derivative, so d dx of c, where c is a number, a constant, okay? When we take d dx of this value here, this is going to become 0, okay? So that's kind of like our constant rule. Okay, so it's important to write down. You can also figure it out like how we did, right? We didn't see an x, so we know that that means that it's x to the 0, and then we used our power rule and we still got the same answer. So this is where being able to interpret and to expand your understanding will help you not just remember what you're doing, but kind of figure things out as you're going if it doesn't look exactly the same as your other problems. So that was our first one. That was our constant rule. Let's look at our next one. So the next one's already completed for us, number 2. And when we're looking up here, we had 5x to the 18. So our function was f of x equals 5x to the 18. As I'm writing this, just like how I wrote y prime over there, that's a tongue twister, I'm going to write f prime of x, meaning that this is now the derivative of f of x. So I'm going to use my power rule where I take my power and I multiply it to the front. So you can see I have my 18 multiplied in the front. And then I'm going to subtract 1 from my exponent. Do your multiplication. So I did 18 times 5 and I got 90x to the 17. This is our answer. You can put a box around it, you can put a star on it, but this is it. There's nothing else you could do here. Let's do number 3 together. So with number 3, we have y equals 4x to the 5th plus x. So now we have two terms. This is our first time that we've seen two terms. So when I'm working this out, I am going to write y prime. And whenever you have more than one term, you're just basically using the same rule or the same property or whatever rule and property you need, because we will be learning more. You're just going to do the same one or whatever you need to each term and kind of treat each term separately. So I'm just going to look at the 4x to the 5th by itself first. So I know I need to take my 5 down to the front, and then I'm going to subtract 1 from my exponent. Then now I have a second term. So my second term was x to the 1st. So that means I'm going to take that 1 down to the front, and then I'm going to subtract 1 from the exponent. Okay, now let's simplify. Y prime equals, so we're going to have 20x to the 4th, and then plus, now x to the 1 minus 1 is x to the 0, which we've kind of already talked about how it's something to the 0 is just a value of 1. So this is really like 1 times 1. If you need to take a side note there, some old news, but we can absolutely take a second to write it down. X to the 0 or anything to the 0 equals 1. Okay, so it's another little side note we have. Okay, so then we can figure out our final answer here. We'll have y prime equals, so we'll have 20x to the 4th plus 1. So that is our derivative of y. Okay, I'm going to put boxes around our answers because it's going to get a little crowded here. Okay, and then we had our y prime equals 0. So first one I did a different color just so you could see that it was a constant. It was a little bit different. Okay, let's do number 4. So again, we have this f of x, so I know that when I'm working on this, I'll write f prime of x to indicate that this is the derivative. And we're going to use our power rule, so we're going to have 4 times 4x to the 4 minus 1 minus 5. And this is really a 1 times 5 times x to the 1 minus 1, and then minus 0 times 3 to x to the 0 minus 1. We don't see an x there, so that's really like x to the 0. So when we're working this out, once you get to a point where you're comfortable, you don't need to write all these steps, but I do suggest writing it out because you don't want to make a silly mistake by subtracting 1 incorrectly. Like we're in honors calculus. We don't want to get points off for not being able to subtract 1. So we have, let's see, we have 16x cubed, and then we have minus 5x to the 0, and then we have minus 0, because that whole term, no matter what we have going on, it's times 0, so it's just going to become 0. You may want to make sure that your final answer is as simplified as possible, so we have 16x cubed. Now we know that x to the 0 is 1, so this is just going to be minus 5, which is like 5 times 1, but it just becomes 5. And that is our answer. You do want to make sure that if for some reason it's not in standard form, that you do put it in standard form, which means highest degree first to the least amount of degrees to your constant. So just make sure that when you are typing it in, especially to Delta Math, it's in standard form. Okay, here we go. We have another one already done for us. This one is a little bit different. We have a rational exponent now, meaning that my exponent is a fraction. So this is the function y equals 3x to the 5/4. When we're doing this out, you're going to take that exponent, multiply it in the front, and subtract 1. So you can see instead of me writing it as 1, I wrote it as 1, but written in a fraction with a common denominator. So instead of writing 5 over 4 minus 1, which could be a little bit more challenging and maybe an additional step, I wrote it as 5 over 4 minus 4 over 4, because that's 1, but it's written in a common denominator. So you can multiply your first two values here. So we have 5 over 4 times 3, which becomes 15 over 4. You can put this in a decimal, you can put it in an improper fraction, which it is, or you can put it in a proper fraction. And then you can subtract 1 from your exponent. So 5 over 4 minus 4 over 4 leaves me with 1 over 4. So let's do this next example with a rational exponent. We have y equals 5 over 4 times x to the 2/3. So we'll rewrite that as y prime equals, we're going to take that 2/3 down to the front, multiply it by 5/4, and then we're going to subtract 1 from our exponent. So we have 2/3, and we're going to subtract 1, but I want to write it in a common denominator. So So I'm going to write it as minus 3 over 3. We're going to simplify what we can. So we have, let's see, we have 2 times 5 over 3 times 4. So that's going to end up being, let's see, we have 10 over 12 x to the negative 1/3. Okay, so a couple things here. We want to make sure that all fractions are simplified. So this ends up being 5/6 and then x to the negative 1/3. And one thing when you are writing your answers, you don't want a negative exponent, okay? It's not an appropriate way to put your answer. So when we write this the proper way, a negative exponent really truly means that it belongs in the denominator. So this is really like 5 over 6x to the 1/3. Our x to the 1/3 gets placed in the denominator because that 1/3 was negative. So one more side note for you in this video, and that's what to do with a negative exponent. Okay, so x to the negative 1 is really like 1 over x. So use that to guide you when you're working on other problems, remembering to put anything that's to a negative exponent in the denominator. So as you can see, the calculus portion of these examples, the calculus parts, really aren't that crazy difficult, right? It's more tedious, it's more algebra work than anything, and it's really being able to look at problems that look completely different and apply the same concept. So your goal is to really just kind of like settle in, really evaluate these problems fully, making sure that you understand and you can apply these skills to future problems.